Okay, so we're going to derive a familiar version of Ohm's law, which says that V equals I times R, where V is the voltage, I is the current, and R is the resistance. And we're going to essentially want to understand that this is just an approximation, but it's a useful approximation because many materials obey this relationship. So for practical reasons, it's fundamental. So we assume that we have a medium and that there's an electric field, and that the electric field is actually everywhere constant, right? So that's already an assumption. And that it generates, right? So you have an electric force, and you have charged particles, and as a result of that electric force, you get charged particles in motion, and that generates a current, and so you have a current density in the medium, which is J, which is proportional to this constant electric field, and the proportionality constant is sigma, where sigma is a measure of how conductive the medium is. So the ability to generate or sort of release charged particles. So to go from current density to current, right, we have to integrate over an area to get the total current going through there. But if the current density is a constant, in this case the electric field is a constant, this is just a constant. We can assume that the medium overall has a constant sigma. That's also an approximation. Then we just get a simple relationship between the current and the current density, which involves the area. So I equals J times A, and we'll replace this with the relationship above. So we get sigma times the constant electric field times the area. And right, so we want to remember that voltage is really related to electric potential difference. So maybe use a slightly different symbol for electric potential difference, which is defined as minus the integral of the electric field over some distance. But in magnitude, so if the electric field is a constant, then we get electric field times a length here, and then of course this is we have to evaluate it over a length, and let's say we get L, and the electric potential is minus E times L, but in magnitude, we call this the voltage. Right? So the magnitude of this quantity is just E times L, and that's the voltage. And so the electric field, the constant electric field in this case, is just the voltage over the length. So we can replace that and make this sigma A times voltage over length. And so we can now notice that we are almost here. We can say that voltage is equal to current times some quantity, which is L over sigma times A. So this quantity is inversely proportional to the conductivity. So the greater the conductivity, the smaller this quantity is, and the less the conductivity, the less the ability to sort of release charged particles to make a current, the greater this quantity. So we call this the resistance, and the symbol for it is R. So we get the more familiar version of Ohm's law, which says that the voltage is equal to current times resistance. And we're going to need this when we get to induction.